Thank you everyone for coming out tonight for this exciting lecture by Professor Farisa Morales. So Dr. Morales is a professor of physics and astronomy at the California State University in Northridge and Moore Park College. She is also a research scientist and astrophysicist at the Jet Propulsion Labs. Professor Morales uses space and ground-based telescopes to observe planetary debris systems. These systems consist of ring-like structures of asteroids and comets colliding, and they give us insights into how planets are formed and the architecture and composition of those planets. Her research interests involve the infrared observation and characterization of planetary debris systems, direct imaging of planetary companions around stars with dust in the terrestrial planet zones, and planetary system formation. In her work, Professor Morales uses the powerful 10-meter Keck Observatory in Hawaii, in addition to the 5-meter Hale telescope at Palomar Mountain here in California. The optics on these telescopes allow her to observe these distant planetary systems while shading out stars. Professor Morales earned her bachelor's degree from UCLA, her master's degree from California State University at Northridge, and her PhD from USC. She is also a reigning karate champion. Is a lesser known fact.
Don't mess with her, people.
Yeah.
Don't mess with her.
In this talk, we'll hear about planetary system formation and the tools and techniques that scientists like Professor Morales use to study these systems. And we will also hear about the ongoing efforts to detect planets in these rings. So if you all help me now, please welcome Professor Farisa Morales.
Thank you for that introduction, Mike, again. As Mike mentioned already, my areas of interest are the study of debris systems around mature stars. So we call those debris disks, or the debris disk phenomena. Even though they may not be a disk, there could be structure in there, like rings, and I'm going to talk about that a little bit in a bit. And also the hunting for planets. After we established, and I was pretty convinced that these disks come in rings, I was wondering what was between the rings, or what was carving out the rings, and so we began hunting for the planets between them. So I'll tell you about that also. Let me start out by, some of you may not be familiar with the planet formation and the motivation behind studying these disks. So let me start out with a brief movie on how we think the overall idea of how planets form. And so we understand, our present understanding of planet formation is that it happens from the primordial hydrogen-rich environment around a baby star. So from a chunk of a molecular cloud, we have, through conservation of angular momentum, the formation of these primordial rich in gas, mostly hydrogen disks. But then within them, we think within the first 1 to 10 up to a 30 million year old baby star, we have the formation of the planetesimals, so the building blocks of planets. After the building blocks of planets have formed, these planetesimals, then planets are also forming in the same environment. Through radiation pressure from the star itself, the gas gets cleared out, right? And so what remains behind is something you cannot blow out with a lamp, is grains of dust. And so what happens here in this other animation is to highlight that after the system is relatively mature, right, so all the gas is gone, but the dust grains remain, then, oops,
I don't think it's playing yet.
Okay, there he goes. Little by little. So what we think is happening within the first 500 million years now, so fast forward from the 30 million, that perhaps planets passing by, shepherding the planetesimals, can gravitationally perturb them, and these planetesimals can collide with each other, pulverizing and reproducing dust in the system that had been already collected into these planetesimals. So let me run that movie again to highlight that. Also, the way this dust can get replenished into these debris disks is also by the sublimation of comets. So it can be planetesimals colliding. Let's see, it's a little slow here. There we go. Planetesimals colliding or sublimation of icy bodies. If these icy bodies get thrown in from, let's say, like a Kuiper belt. So this is all reminiscent of an early solar system. So reminiscent of the late heavy bombardment, for example, which happened around 750 million year old solar system. So within the first billion years of existence of the solar system, Jupiter and Saturn are thought to rearrange themselves a little bit and throw themselves a little bit out, disturbing the Kuiper belt. Uranus and Neptune, flip places, and the Kuiper belt objects get thrown in, and so you're going to have collisions and sublimation of ices in the interior regions of a newly formed planetary system. So this is all happening within the first billion years. All right, the things that are, or the features that are easier to observe, can you guys see this laser here? Is that when you have a collision, this is like fast forward, when you have a collision of planetesimals, that dust will tend to get spread out into ring structures, all right? And that is a lot easier to observe, especially in infrared radiation, when these grains are being thermally heated up by the radiation from the star, and so these grains absorb the radiation, re-radiate it in infrared, and so it's a lot easier to see these rings rather than the tiny planetesimals, because all that dust when accumulated, has a very small surface area, and as you know, how much something emits, it depends on its surface area. So when you spread it out, it's a lot easier to see these rings. So these rings are the ones that we've observed with infrared observatories like Spitzer Space Telescope, the Herschel Space Observatory, and other tools. So when I talk to you about debris disks or share this type of research, I'm really referring to, here's a cartoon depiction of a planetary system with debris. So here's a star in the middle, all right, ish. A warm, perhaps like what we have here, an asteroidal belt. Also a colder Kuiper belt. In between we have terrestrial planets, we have gas giants. Here's a representative of the asteroid belt. Here's a representative of the asteroid belt Pluto, right, series. And also the debris left behind from the sublimation of comets and collisions among these things. So it's all that zodiacal dust that we see here in the solar system as well. So it's everything, including you and I, we're all debris from the formation of the sun. For the moment, I'm going to concentrate on the dust, since I'm not able to find people or things with antennas elsewhere. So the motivation behind this project is to compare, to look for this dust, and is it also in ring systems like what we see here? Does every star have debris, right? Can we establish that with observational evidence? What's the composition of this dust? Does it look like anything we have here? Is there dust enough in the habitable zone, for example, to form the terrestrial bodies that we see here? And are there gaps, multiple components, and that kind of thing? And then connected to planets, right? So how do they interact? Are these planets carving these belts, or do the belts form there first and then the planets form around them, or what's going on here? So we really are trying to understand the planet formation processes by studying systems at different stages of their lifetimes to see if we can put the story together. So here's some of the data, what factors inform this kind of effort. And so for many of you, how many people have heard of a black body? Very good, so the majority, how many people have never heard of a blackbody curve? All right, so there's a few, and this is why exactly I have this slide. So imagine you have a point source, here's a star, okay? And what you expect to see from that star is this characteristic curve, all right? So for most of you, you've heard about this before, but what this is showing here, for those of you that have never heard about it, is how bright is something versus wavelength. And wavelength here is increasing, getting longer and longer towards the right. Right, so for a star that is very hot, for example, the sun is almost 6,000 Kelvin, 5,800 or so. There are obviously hotter stars, cooler stars than that. Characteristic of their temperature, they will emit most of their radiation, right? That peak happens at some wavelength, right? For the sun, it's in the optical wavelengths. And so further to the left, you have shorter wavelength radiation, like gamma, X-rays, ultraviolet. And then further out, what we call the Rayleigh gene slope on this side, we're going to have infrared photons and radio waves and so on. So cooler and cooler temperatures for these particles. So that characteristic curve is called a blackbody curve. Now imagine that we put a ring of grains around a star, and they're all at the same distance, so therefore they all reach the same temperature because they're in thermal equilibrium with the star. And so imagine a ring of debris, all the grains at the same temperature. What you're going to have when you observe this system is the radiation from the star plus the superposition of another black body, which is the sum of all these grains in your spectrum, or your what we call the spectral energy distribution. And so I'll give you an acronym really quickly. So spectral energy distribution, SED, for short, refers to how much flux are you seeing, how bright is something versus wavelength. So what we saw with Spitzer Space Telescope, here's a plot from a 2011 article published by yours truly. We're seeing, I'm going to zoom in here, where I see the Rayleigh-Jean slope of the Blackbody Curve, all right? But yet something else is happening. It's like it's peeling off the photosphere. So from the photosphere of the star, you would expect that slope, yet you're going to see something else rising like that. And so that's a hint that there's some dust around the star. And so focusing on this little segment here, here's our flux in Janskys, right? So some units versus wavelength, 1 micron, 10 microns, 100 microns. So I'm going to focus there. And that line right here, the gray one, is the Rayleigh-Jean slope from the photosphere of a star. Okay, that's what it should be doing. With Spitzer, we looked at sources like this one, and we saw many had this type of data. All right, so this is from the IRS spectrometer from 5 to 35 microns, from about here to here. It's not coming down. It peels off around 10 microns or so. It's like, oh, that's interesting. Clear evidence that there's warm dust. How warm? Well, I'll tell you. I drew a histogram of what's the temperature of the dust around here. And so it turns out, for first exercise, I did this, right? So what if I have the black body of a star for a star and a black body representing the grains, and one black body extra superimposed with the star was not enough. And so if you can see, what I'm going to show you next is I'm going to subtract the contribution of the star, so all this flux here, subtract it out from the data, and I'm going to plot only the residuals. So then that looks like this. So now the star, basically that gray line becomes here, the horizontal line, and what you see plotted here is the excess emission, so above what is seen from the star. This slope does not match that fast climb of a blackbody curve. And so we tried one, but it wasn't working. But if we try two, pretty good fit. So for example, here, all right, here's a warm belt, or the contribution from a warm belt, the contribution from a cooler belt peaking at longer wavelengths. And if I subtract, for example, the contribution of the warm belt now, the excess, after subtracting the star and the warm component, I get this, right? Very nice fit to a cold outer component. So I have clear evidence here that I need at least 2 black bodies to reproduce the data, or reproduce the observations. By the way, so this is IRS spectroscopy, and then we have the MIPS photometer on board Spitzer. So this is at 70 microns over here. So if we detect anything at 70 microns, that means it's like 50 Kelvin dust, where something that's peaking here in the IRS wavelengths, it's something that's asteroidal in temperature. So I'll show you what that looks like. Here, so I did that exercise, and back in 2011, I published a histogram on these things. So we studied 69 sources, almost 70, and I plotted them solar type stars on the top histogram and A type stars, which is 2 to 3 times more massive than the sun. All right, if you're going to be 2 to 3 times more massive than the sun, you're going to be way more luminous, about 50 times more luminous than the sun. So what if the debris around more massive stars is a little different than the solar type stars? It turns out they're the same. So I have here about 20 solar type stars and about 50 A type stars. And if you plot how many versus temperature, this is the dust found, these blackbody curves. The warm dust tends to peak around 190 degrees Kelvin for either solar type stars or A type stars. And the cold dust is peaking around 60 degrees Kelvin. Asteroidal and Kuiper-like temperatures. So this was an observational result. I was awarded a medal at the American Astronomical Society. It was a Chambliss Award. And again, this is an observational result. This is nature talking to us, telling us that there is a common temperature horizon where the dust tends to pile. It doesn't matter if you're a little star, you're not so luminous that, or if you're a very, very luminous star, that the grains will get pushed out such that they pile up at a specific temperature. So for not so luminous stars like the sun, the rings will be smaller such that they're at the same temperature as, stars with bigger rings. And so that was a hint that this has to do with composition of the grains, not how much mass was there to begin with, because these A-type stars, for example, are only like 2 to 3 times more massive than the sun. All right, so it was a temperature thing, not necessarily just the spatial distribution or the architecture. So as I was going through my dissertation at USC, I was a PhD student. I applied to use the Herschel Space Observatory for all these sources that we had evidence of two belts, especially warm and cold components. And what came back after getting the proposal approved and so on and doing the observations, we got lots of donuts everywhere. Donuts everywhere. It's like, oh my gosh, Herschel Space Observatory, by the way, it's complementary to Spitzer in that it was observing with a PAX instrument at wavelengths that were cooler than the 70 micron detections we had with Spitzer already. So this is 100 micron detections, 160 microns, giving us more information on that spectral energy distribution that I was showing you earlier. So we got all these donuts, right, face on, and there's a lot of inclinations of all variations, which is a healthy check to get these guys. And so what we're seeing here is the outer belts, right? So we have enough resolution to see exactly where the outer dust is, the Kuiper belt. So these are all Kuiper belts seen with Spitzer. These are a few from those 70 sources-ish that I was telling you about. And so now you have more information, not only about at the longer wavelengths, how much is that Rayleigh gene falling off, all right? Is it Rayleigh gene on the slope of that black body curve, or is it something else? And it turns out that it was something else. So let me show you what that SED looks like. So in order to do the spectral energy distribution modeling again, it turns out that black bodies failed, and I'll show you how. And so I had to introduce realistic grain properties. And so I adopted something called inhomogeneous grains, because here in the solar system, we have icy grains in the outer regions, right? We have volatiles, we have water, ammonia, carbon dioxide, carbon monoxide, we have all kinds of grains. This is a picture of about 3 micron diameter of a early grain here in the solar system, and icy particles are seen in protostellar sources as well, and Kuiper belt objects here. So then I had a choice. I said, well, at that point, there were a couple of, one kind of grain that was being explored mathematically, which was the CMP grain. CMP stands for core mantle particle. So there's a mantle around a silicate core, right? So you have a rocky inner most of the mass is in this inner grain, and then you have this thin layer of volatiles. Or what if we have volatile or particles that are icy also, and I decided to call these IMPs. IMP stands for inclusion matrix particles. And what would be the difference between these grains? So inclusion matrix particles is, imagine a matrix of ice. It could be dirty ice already, or just pure water ice. So we model these things as well. And then put inclusions in there of silicates. In fact, this is actually a little bit better to use. And I'll tell you the punchline about which one was better in terms of these grains and how they're behaving, their emissivities once I computed them, and I'll tell you a little bit more about them. They were the same. They really are not very different. There's slight differences, but not very much, not enough to be resolved by the data we had. Very, very little difference, negligible. And this kind of grain is actually a little bit better to adopt because you can put inclusions of vacuum, right? So you can make fluffy grains, porous grains, where you couldn't do that with these mathematics for the other kind of grain. All right, so here's my model. So if you thought you were coming to an astronomy presentation and you were not going to see an equation, you were wrong. So Michelle told me to keep this for the general public. There's a lot of engineers that may not have seen astrophysics presentations before or so on, and all levels. So I'll show you an equation. So for those of you that like the math, here it goes. But for those, don't leave. For those of you that don't like it, hang in there. There's not too much of it. All right. So here's the cartoon picture of what I'm modeling. Star in the center. All right. A warm asteroidal belt. A cold belt, and I'm going to assume that the distribution of the grains at each belt is not infinitesimally thin anymore, because with a black body, it would be an infinitesimally thin belt. Now let's assume that there's more or less of a Gaussian distribution, center at R0, right, with some width, which we initially just throw in. What about like 10% the radius of this ring, all right, for the width? We know that the astrobelt, has about a 1 AU width. It's about 2 to 3 AU, and then the Kuiper belt, who knows, we haven't really pinned it down, but like 40 to 60 AU, that kind of thing. So these belts could be broad, at least from what we see here. That could be also a free parameter in your fit, but for the moment, let's just assume like 10% the radius. And so that's where this Gaussian, that's what that means. And then let's put in here the CMPs and the IMPs, and let's compute what's going on, see if we can reproduce the data. So what we've done is we assumed, again, the Gaussian distribution. We also assumed that for the grain sizes that there's going to be little tiny grains and then bigger and bigger and bigger, and all the way to, like, you know, you can, when do you stop? Boulders and planet-sized things. So we cut it out. We said the grains that are contributing to the flux are the tiny grains, because those are the ones that get all smeared out, right? All the way to like millimeter size. After that, they're too big, they're not contributing, they don't have a lot of area, so they're not contributing a lot to the flux. So we cut it off at like 1 millimeter, and we thought this is a good representation for the model so far. So we adopt a collisional cascade slope, negative 3.5 here for the grain size distribution. There's a lot of little grains and then less and less and less of the bigger grains, which is typically what you find anywhere you go. You go to the mountain, grab a bunch of dirt and say how many bigger things you have, and there's more and more of the little guys. All right, and so we put in our A min and A max, and A min is limited by how small can the grains get by something called the blowout size. So there is a size that if you're smaller than this, the radiation pressure from the star is going to blow you away. All right, so that's computed from the luminosity of the star and the properties of the grains. And so we put all these things in here. So we have a double integral. Here's the math, a little bit of the math. So you have the flux per unit wavelength, or per wavelength, is, d is your distance to this object, double integral in r for the radial distribution, right, and a for the grain size distribution. This epsilon here means emissivity, which depends on the size of the grain and at what wavelength. And then here's the Planck function again, but now the temperature of these grains is determined by the size of the grain and where it is, and so on and so forth. So this guy, C, goes in here, and let's see, how did this go? That guy goes in there, and anyway, you put that in there, and so your equation comes, it's a little bit more elegant, and it keeps growing, right? And it just keeps getting messier and messier. You're like, okay, but you know what? This is what computers are for. Yes. I didn't have to do this by hand. Like, excellent. This is what computers are for. Let me highlight that this temperature of the grains, I computed a priori. I just built a whole library of these temperatures because it's very time consuming. All right, so I was urged many, many times to just go to the supercomputers, like, no, I can't get my laptop to do this. Let me just kind of build these libraries separately and so on. So anyway, I run this model for each of these rings. So the total model is the contribution of the flux from the star, plus the warm component, plus the outer component. And so there's only 3 parameters so far. How bright is the star? So the photosphere of the star, these are, pre-computed synthetic photospheres for stars, or just how bright is the star, that's a normalization factor. And then how bright is the warm rings, that's another normalization factor, and what's the location of the ring, that's the other free parameter. And for the outer, same thing, how far away is it, that's a free parameter, and how bright. Right, so you only have 3 fitting parameters in your optimization, and here's the results. Oh my gosh, lots of lines. Let me walk you through it, but don't be too intimidated because you've seen this before. All right, so let's highlight the upper plot for now. Here's the star. You've seen that before. Here's the data, for example. This is for a specific star, HD159. They all have phone number names. Okay. And IRS spectroscopy, right, from 5 to 35 microns, MIP 70 microns, Herschel 100 microns, and Herschel 160 microns. And the green curves here, which are 1, 2, and the sum of those 2 is the green model going through there. I don't know if you guys can see that. If I subtract the star, so we subtract all this contribution from the star, now I have the excess emission here. Noticing the green lines again, so here's 1, all right, and 2, and the sum of those 2 green ones are this green line right here. 2 black bodies does not go through the data. All right, it goes more or less to the IRS spectroscopy data, spectroscopic data, but it misses the MIPS 70 and Herschel 100 and 160 micron data. So by adopting the realistic grains that I was mentioning to you, I skipped that part where I take the optical constant, so the refractive index, and so basically you get these numbers from chemists, how does silicates work, and IC, and so on and so forth. And I combine these things using effective medium theory, and then you compute their emissivities, and you put them in your long equation, and what you get, for example, if I adopt 2 rocky belts, right, so just rocky material silicates, astronomical silicates we call them, you get the pink curves, the magenta. All right, so here's one, and here's another, and then the sum is that pink curve right here, or through there you can see it, and again it fails. All right, what if I make the outer belt icy? Now those IMPs that I was telling you about, make the matrix icy and then put the inclusions of rock material, 50% volume fraction, and now you get the blue curve, right? So there's the two blue components and then the sum goes right through the data. It's like, yes. So I have evidence based on the shape of the spectral energy distribution that the outer belt is icy. The inner belt, I always use rocky material because the temperature of the inner belts is so high, it's above the sublimation temperature of icy grains, so above 120 degrees Kelvin. So those tend to be like 190, 200 degrees Kelvin. Ices have sublimated by then. But the outer, right, is always better fit by icy grains, at least for the majority of resolved systems. Let me show you another one, right? So this is one of those guys to illustrate the point here. Oh, I'm so proud of that I made it bigger. Right, so exactly this part is like, look at that, it's bigger. Yes. Let me show you another one. And let me make it bigger. So that part again, it goes through the data. All right, it kind of misses that point there, but the pink, all right, it's just not good enough. Two rocky belts is not good enough. Not to mention black bodies, it just completely fails. By the way, this star HD16 is one of my favorite ones. It's only like 13 parsecs or 14 parsecs away. And it's a solar-ish type star, K0. And let's see, so it's a solar type star-ish, meaning that the blowout size of the grains are so little, they're like, less than half a micron, that you're starting to get spectral features, right? These kind of shapes there, a 63 micron feature in ice or so, right? These are things that we can probe in the future to establish that, more with higher confidence that indeed it is ice. But for the moment, I have evidence that it's ice based on the shape of the SED. So to wrap up the first part of this presentation, Spitzer clearly characterized the warm dust from 5 to 35 microns, right? Most of the time we don't see spectral features, it's just the continuum. Spitzer also detected the cold components, right? But Herschel came back and not only confirmed that there's a cold belt, Kuiper-like material around many stars nearby. This is all within 150 parsecs or so survey. The cold belt is there, and based on the shape of the SED, it also resolved the location of the grains, which helps us pin down some of the degeneracies in the modeling. If you know where the belt is, then you can say something about the grains. Because if you don't know where the belt is, it turns out that little grains, if you have them very, very far out, they're not going to emit long wavelength radiation because they're physically so small that they cannot emit radio waves because, again, they're just physically too little. So there is a degeneracy in SED modeling, but once you get the size of the belt, you know exactly where it's at. All this is clear. We know exactly about the grains. We have higher confidence on the grain composition, and so revealing the presence of water ice in these belts. By the way, the ice that I used was what we call dirty ice from Pribish et al. It's a combination 3-to-1 ratio of H2O versus NH3. And so, that's representative of what we see here for comets. But if I went to talk to comet people at JPL, because they're just like the next building. That's one of the greatest things about JPL. You just walk over to the next building and you find experts in different areas. And I asked them, like, what is the composition of these grains? And they're all over the place. So we just grabbed something that was more or less in the middle representative. All right, and if we have belts, there's gaps. And that's what triggered the next part of my work here, and what I'm going to share with you is what's in between these belts. Here in the solar system, we have 4 gas giants. Are there gas giants over there? So I proposed to Keck Observatory to go look at these guys and do high contrast imaging using a coronagraph on NERC2 on the Keck Observatory. And we went planet hunting. This is in the Big Island of Hawaii. Keck is most of you may know already. So it's located at the top of Mauna Kea. This is like 14,000 feet high, 40% the oxygen, and there's these things up here. This picture is taken from Waimea. Obviously, fortunately, there's remote observing facilities here and in Waimea, so closer to sea level. I took a picture over there back in 2012 when I went there for the first time, and I was like, "Aloha, take a picture," because I'm like fainting at 40% the oxygen here. So you're advised to take aspirin when you go up to those altitudes. If you take aspirin, it thins your blood, and it's easier to get up to your brain. So the jeeps here are like smaller than, can you guys see the jeeps right there parked? Amazing observatories. So I got granted time. Here's, oh my gosh, what a narcissistic slide. And there's 2 pictures of me. I'm like the size of one of the 36 hexagonal mirrors on the primary mirror here on Keck 2. And I'm actually, I'm a little bit bigger than one of the mirrors, but you get more or less the idea. It was really hard to get a picture of this thing because, you know, interestingly, I went up there for the first time, right? And I went to visit the telescope. And so the people there are very friendly, and you're sharing with the people that maintain, engineers that maintain the telescope. And typically telescopes are stowed vertically up during the day. And so they gave me a hard hat, and I climbed up to the catwalk, which is this thing in the inner side of the dome. So it's like 2-3 stories high. And I'm walking around it, just looking at it. And it's this amazing monster that I'm going to use that night. And all of a sudden it begins to tilt really slowly. And I looked around like, I swear I did not touch anything. And I was kind of like, okay, I guess they're doing maintenance work and so on. So I just kept walking, and because it was tilting, I'm like, I'm going to go see the mirror, the largest mirror on the planet. Like, mirror, mirror on the telescope. And so I went to check it out. The phone just doesn't do it justice. Like, you know, you try to fit a picture. Here's the secondary mirror, the primary. You just, like, you cannot fit it in one picture. So I walked around, and I said, okay, let me now take a picture sideways. So I started to walk around to take a picture sideways, and all of a sudden the thing continues to follow me. And I'm like, okay, maybe they're testing that way, so I'm going to go this other way. And the thing followed me this way. And then I took a step over here, and it was following me this way. And then I heard the giggles down there. And I'm like, I can hear you. So they were playing with me. So they have fun with you if you go up there, too. I was so scared. Anyway, this thing, you know, cost $100 million to build back in 1990s dollars, right? So I could not replace it even if I tried. Here's what data looks like. So that first night, I take a picture of, there's not even a coronagraph yet. And there's a source there. CNET K-band, H-band. So K-band is like 2.2 microns. H-band is like 1.75 microns or so. And we're seeing a source, right? So very, very interesting. Let me show you what this data looks like. But before I show you what the data looks like from Keck, let me highlight this coronography technique. A lot of you may know this, especially because I'm talking to a lot of engineers, but I know there's at least one kid in the audience and a few more about AO imaging. So Keck has an AO system. AO stands for adaptive optics. And Palomar also has been retrofitted with adaptive optics system. And I borrowed a movie from the Gemini Observatory, because I could, you know, this is the only one I could find. There isn't one for Keck, unfortunately. We need to start working on that one. And what I'm showing you here is how the AO system works. I could not believe how it works. So we're going to get rid of this dome from the Gemini Observatory for the moment, but it works the same way. So the starlight is going to come in to your observatory. So let's point the observatory there. It's going to bounce off the primary mirror onto the secondary mirror and back down through that hole onto your optics box. I could not believe that it works. So what's going to happen now is that this light is going to get bounced around your optics box, and it's more complicated than what is shown here. But the point is that it's going to bounce off of this mirror called the DM, a deformable mirror. Lots of acronyms, right? So the deformable mirror, what it's going to do is it's going to catch the photons wherever they were supposed to have fallen in, right? So here, here, there. Once you close this loop, right? So when you close the circuit, which is monitoring the turbulence outside, this deformable mirror now begins to warp, all right? Sends the corrected light to your computer, and you go from a fuzzy image to something that's 1,000,000 times better resolution. Amazing. When they explained this to me, I was like, nah. Really? Without this, I couldn't do what I do, right? 1,000,000 times higher resolution, are you kidding? And this deformable mirror, by the way, misshapens itself 1,000 times a second. 2,000 times per second. I mean, this is amazing engineering. Thank you guys, all the engineers. Thank you. I had the opportunity a year ago, last summer, to take a few students. I had lots of minions helping me around take data. So I've been going about every semester or so. Going up the hill was kind of fun. They were taking data down at the Waimea Control Center. That's what the screen looks like when you're first looking at it. There's your coronagraph. So your coronagraph is covering the light from the source, looking for faint things around it. that's what our results look like, right? So this is after reducing the data, doing CLIP and Loki and all these like optimization routines, which some of you may have heard about. We have lots of candidates. Some of them precisely at the locations where I would expect between two belts. So I know where the belts should be, but they're not very bright. They don't show up in these images, the belts themselves. Because remember these belts, you're picking them up at 10, 35, 70, 100 microns, not at 2 microns, right? So 2 micron emission, it would be very, very warm. And these grains are in belts that are a lot cooler. So those belts are not here, but I know where the belt should be, their spatial distribution, especially for those that I know where their inclination is and position angle in the sky, because I saw it with Herschel. So some of these are precisely where you would want them, or you would expect them to be. So the missing data in the middle is, again, the place where the coronagraph is. And next to that will be kind of noisy, right? So if you think you have a candidate, it really has to be above the noise level. So here's a candidate. So the way you pick them out is, well, it has to be like a roundish source, right, with a good PSF or point spread function. And so that looks like a candidate. That looks like a candidate here at some distance. Another candidate there, and so on and so forth. So you see them circled there. So the exercise now is to follow them up, wait a couple years to make sure that these point source faint candidate companions are co-moving with the star, so they have the same proper motion-ish, right? Because they're also moving or rotating around the star. So there's ways to compute if they're not a background source, because it could be a star in the background, right? Very, very faint, and just co-position in the sky because you're so lucky, or I'm so lucky, right? And those we have found lots of. So those are candidates that we're still following up on. I want to, well, here's a couple of results. So not too long ago, with Dimitri Maue, who's a professor here at Caltech, here's the discovery of a brown dwarf. So not only are we finding gas giants, we're also finding brown dwarfs, right? So a little bit more massive than, like 13 times more massive than Jupiter, up to like 80 times the mass of Jupiter. That's the range-ish of brown dwarfs. We're also finding white dwarfs. So we're finding all kinds of things that are gravitationally associated with the primary star here. There you go. So here's a white dwarf we just published like last month with CREP. And another mention I wanted to offer or to share with you is that we're doing the same thing from Palomar Observatory. All right, so from Palomar, it turns out, I'm going to highlight a couple of results. For example, this guy has what it looks like 2 circle-ish point sources, candidates, within the outer Kuiper belt location, about 90 to 100 AU from the star. We're following up on that guy. Again, we saw that one from Palomar. And so again, this is a candidate. We haven't confirmed it yet, but it's in the list. And then something else, I don't expect you to read this poster, but we're gonna focus on this image. Palomar is the only observatory on the planet that, because of its optics bench, the way it's set up, and because of one of the designs of Gene Serabin at JPL, he said, let's do 2 coronagraphs to be more efficient at covering the light from the star. And these coronagraphs that they're working with are called the VVCs, or vector vortex coronagraph. So this setup is called the SDC double coronagraph, stellar double coronagraph. But in reality, we call it the super-duper coronagraph for SDC. So using the SDC setup, the only place on the planet where you can do this, 2 coronagraphs lined up, what we've done is is this a word, disalign them? Or unalign them? What do you, disalign them? Something like I'm inventing English now. So take them off alignment and now tackle for the first time binary stars. So we're looking for companions around close binaries where we can use those 2 coronagraphs and look at the star system, because again, most of the stars out there are binary star systems. And so these are a few candidates that we've identified using the SDC, the super-duper coronagraph, or the stellar double coronagraph, designed by Gene Serabin. Here's a companion. It looks like a companion on the So you can have planets that are circumbinary, circumprimary, or circumsecondary. And so this would be circumsecondary if that's true, or it turns out to be real. Here's another guy. Here's another guy. These 3 don't seem to have anything, and the bottom 3 do. Here, here, and here. These things are 5 sigma above the noise level at that location, even if it doesn't look like from how the image is shown in the projector, but these point sources are at least 5 sigma above. So, you know, our confidence is high that it's something. It might be a brown dwarf, a white dwarf, a background star. So we need to follow those up and confirm. So that's so far what's going on with hunting for planets around dusty systems. These are all debris disk stars. So we know there's a lot of material there that is being perturbed, perhaps by companions, or it's a late heavy bombardment kind of era. And here's a nice picture of our Milky Way galaxy as seen from Earth and the zodiacal dust from our own solar system. Thank you.